Okay, let's start. Okay, so what we'll do today is I have a bunch of practice problems, right? So some of them are pulled from the existing practice problems that have been shared on the portal, and some of them are new. So we will go over these problems in the sense we'll try to solve them, and in the process we'll bring up concepts that are required, right? So we'll go over the fundamental concepts that are required to solve that problem, and hopefully that will act as a revision, right? So the problems are not in any weekly order, right? They're all jumbled up, right? So you will see suddenly some question from week 1, some question from week 5, and so on, right? So that's the plan for today. So Tuesday we'll have a session by Arun sir, right? So that will act as one more revision session. So there you can ask uh, another set of questions, and then later on we can decide when to have the other session. Okay, so is the plan okay with all of you? Can we go ahead and start?
Just one question, Karthik sir.
Yeah,
The syllabus will be from week 1 to week 11, or week 12 will be included as well?
full syllabus, week, all 12 weeks. So all 12 weeks, the last 4 weeks will have 60% weightage, and the first 8 weeks will have 40% weightage.
Okay, thank you.
Sir, can you please share the YouTube link right here?
So it is one, I think.
Okay, sir.
Okay, so we'll get started now. The first question is this, right? So we'll start with logistic regression. That's week 9. Okay, so you have a logistic regression model, and the threshold for prediction is t, right? So if you recall, logistic regression models return a probability, right? So they return some probability as their output, and depending on a threshold that we set, you can determine the final predicted label of the model, right? It is 1 if it is the probability is greater than the threshold. The probability turns out to be less than the threshold. The predicted label is 0. Okay, so this is the idea of thresholding in the case of logistic regression models, right? So that's the simple setup. Now we have to find the decision boundary of this model, right? So you have to find the decision boundary of this model. So how do you think you'll approach this problem?
I guess we'll. Okay, so am I audible? Is it?
Yeah, yeah.
So I guess we'll have to just apply maximum likelihood and the sigmoid function to get the optimal W's, and just W transpose X would give us the decision boundary, I guess.
Okay, okay, that is one answer. Any other? Does anyone else want to attempt? What do you think is the approach? So did everyone understand what the question is about?
Can we equate with the sigmoid function 1 by 1 plus e to the power minus z equal to t, and then we will get the value of z. Then that will be the answer, I guess.
Okay, yeah, that's correct. So that's the way to proceed. So let's go over a few basics, right, to understand this problem, right? So first thing is, what is a decision boundary? What do you understand by the term decision boundary? We have used it so much, right, in the course.
Classifier kind of thing, like one side one kind of object and then other side other kind of object.
Okay, okay. So this line is what? In the sense of a linear classifier, what does this line represent?
That's the perceptron line. I mean,
W transpose X.
Okay, so this is what we call the linear classifier, right? So it could be a perceptron, it could be SVM, could be logistic regression, right? So, but the fact is, all these are linear classifiers, and this line represents a classifier, right? So a point now comes up for prediction, right? So let's that black color point, let's say, comes up for prediction, and after evaluating it using the particular model that you have, let's say it turns out to be 1, right? So this side belongs to 1, and likewise you try it out for one of these points, the classifier predicts 0, right? So now you'll repeat this process for every single point in this space, right? So in this case, all the points are in the plane, right? So you'll repeat this process of taking a point at random, asking the classifier what the predicted label is, and you will color the point appropriately, right? So you will end up with this kind of a color, right? Do you all agree? This side is positive class and this side is the negative class. Okay, so what are
Okay.
these?
Hi, sorry to interrupt.
Yeah.
Is this convention always followed? Like if we have 1 0 labels, then the left side of the classifier is always 1 and the right is 0. Is this
No,
convention always followed?
no, right? So you have to also look at what the direction of the weight vector is. I have ignored that for now, right? So depending
Oh,
on your classifier is actually determined by the direction of W. So which side is green and which side is red depends on where W is. Right? W will be perpendicular to this line, but if it is in this case, assume that it's pointing in the northwest direction.
okay.
Okay,
got
northwest
it.
direction. That's
Sir, sorry to interrupt you here. I have one question here. Suppose I have data in the third quadrant, sir. Okay.
okay.
Okay. So in third quadrant, I have a positive data, positive points, you can say. And in the first quadrant, I have a negative points. Okay.
Okay.
So generally what we do while defining W, my W is actually in the direction of the positive data point side.
Right, right.
Right. So in that case, my W will be in the direction of third quadrant, correct?
If you said third quadrant is positive data points, right?
Yeah.
Yeah. That will be the direction of roughly. That will be the direction of W.
Yeah. So third quadrant will be direction of my W.
Correct.
Okay.
Yeah.
So sir, how do I know? When we mostly we do, right? The W transpose X greater than 1, that will be positive thing. So I mean, I'm not able to picturize that part, sir, in that case. Okay, because direction has been changed. Okay, so when you draw everything in the positive direction, I mean, suppose if the positive points are in the first quadrant, in that case, I can understand. Okay, W transpose X greater than 1 will be positive, and less than 1 will be negative, sir. But in my case, I just reverse the scenario. So W will be now W will be pointing towards the third quadrant. Okay. So in that case, what condition I will write, like W transpose X will be equal greater than 1 will be positive? Will that still be valid in this case, sir?
Yeah, that is still valid, right? So only the direction of W is changing. The W transpose X greater than 0 is 1 is still the rule, right? That's the rule. So we'll hold on to your question. We'll come across different configurations of W. So
Yeah.
here I have not drawn W, but yeah, you will come across different configurations of W in this session.
Yeah. Thank you, sir.
Okay, so see, this is the decision boundary, right? This is the decision boundary, and these are called decision regions. That's the general idea. For any linear classifier, this is the basic setup. Now, what have we been asked in the question? We have to find this decision boundary for this logistic regression model with a threshold of t. Okay, so do you all recall that this is the formula for determining what the predicted label is in the case of logistic regression? Right, so if the probability of y equal to 1 given x is at least t, then you return 1 as the predicted label. If not, you return 0 as the predicted label. Okay, so what is P of y equal to 1 given x for such a model?
The sigmoid function, I mean, the sigmoid function evaluated at x.
Evaluated at which point? Sigmoid function is correct.
Yeah, so we can.
At the given point, the point that we're trying to predict.
Okay, so is it sigma of x? Assuming sigma is the sigmoid function, is this probability equal to sigma of x or something else?
Sir, at the
Yes.
T,
I
I
mean,
think T.
threshold point, sir. So
It's sigma of W transpose X, right?
Correct, right? So it's sigma of W transpose x, right? So we are trying to find the probability of y equal to 1 given x, and that is sigma of W transpose x. Now, this is what we have to find if you want to find what the decision boundary is. This is what you have to compute if you want to find the decision boundary. Now, do you all agree so far? Are there any questions? Please stop me here. If not, we may
sir,
never.
what will be value? So, what is the probability for like when the W transpose X equal to 0?
You tell me, no? So think about W transpose X equal to 0. If you plug it into the sigmoid function, what will you get? Sigma of 0, right? What is sigma of 0?
Okay, so 0.5, I think so. 1 upon 1 plus then 1. Yeah, 1 upon 2. I think 0.5.
Correct. Yeah, that's right. Right. So did everyone get this part? If you want to find the decision boundary, you have to. So what is peculiar about the decision boundary? If a point falls on the boundary, what do you think is going to be the label? What is the predicted label of a point on the boundary?
On the boundary.
Okay, that's the convention. But in general, can you say with absolute certainty that it will be 1?
But if the point falls on the boundary, then the sigma of W transpose X would be T. And here you can see that y cap equal to 1 when P of y equal to 1 given is greater than equal to T.
Correct,
So
right. Yeah, I get your point now, but I'm asking in a more general sense. If a point falls on one side of the boundary, it is 1. If it falls on the other side of the boundary, it is 0. But if it falls on the boundary in general, right? Forget about this particular equation or inequality. In general, what can you say? It could go either way, right?
yes.
Right. So that is one that's the characterization of the decision boundary, right? So it is that part of the space where you are like not sure about, you're not like 100% sure about the decision, right? So this is going to be P of y equal to 1 given x equal to T. Okay, so did everyone get why we have equated this to the threshold T here?
Yes, sir.
Okay, so how do we expand this? What is the next step here? This expression that you see here, how does it expand to? How does it?
To write it in that form, to use the sigmoid function 1 upon 1 plus e to the power W transpose X.
Okay, so we'll do that. 1 by 1 plus e power minus W transpose X equal to T. Now, how do you simplify this?
Maybe we'll just isolate e to the power the exponential term and then take log on both sides.
Correct, right? So we just take the reciprocal, we do 1 by T, and then we can subtract 1 on both sides. So we get 1 by T minus 1 is equal to e power minus W transpose X. Now we can take log on both sides, and we end up with minus W transpose X equal to ln of 1 by T minus 1. Okay, I hope that part is clear to all of you. The sequence of steps that we have done. Okay, so finally we end up with W transpose X equal to some quantity, right? Don't worry about what this quantity is exactly, but this is what we get. Now, usually what is the threshold in the case of logistic regression?
0.5.
0.5, right? So if T is equal to 0.5, what does the RHS become?
Zero.
Yeah, that's correct, right? If T equal to 0.5, this is ln of 1 by half, right? 1 by half. So ln of 2 minus 1 or ln of 1, ln of 1 is 0, right? So if T is equal to 0.5, this is the decision boundary you get, right? So it passes through the origin like every other decision boundary in our course, right? So this is quite clear, right? We are familiar with this. Now, if you set the threshold to a high value, right, like 0.8, what do you think is going to happen?
Decision boundary will shift towards, I think, left.
Okay, so if you, in terms of direction, can you tell me northeast, northwest, southeast, southwest?
I think northwest
Okay.
in the positive direction.
Okay, so if T is high, then it will shift to northwest, you're saying?
Yes.
Okay, if T is small, very small, let's say 0.2 like that.
Then it will go in opposite direction, in the negative directions.
Yes.
Towards.
Okay, right, so that's correct. No, so notice what happens. Again, the solid line is the decision boundary. So if T is 0.8, this evaluates to W transpose X is equal to 1.38, right? So this shifts here, and if T is equal to 0.2, this shifts here. Okay, so practically speaking, what does a high threshold mean? Your threshold is high, what does it mean?
It means basically that we are basically, in medical terms, if we can say through an example, that if the probability of saying someone that you got a cancer, then it might be devastating for him. So that's why we set the probability to be higher.
Okay, right. So
Like we want to be more sure.
exactly, right? So that's correct. So we want to be absolutely confident before we make a prediction, right? So that's why we set the threshold to be high, and therefore it's not enough if the point is away from W transpose X equal to 0. It should be away from this line W transpose X equal to 1.38, right? That's what it means. On the other hand, if T is small, 0.2, then what we are doing is some kind of the opposite thing, right? So you could think about it as we are predicting a data point to belong to the label 0 only if the probability is greater than 0.8, right? We are doing it for the label 0, or if you are still thinking about the label 1, then we are setting the threshold to be very low, right? We are like passing all data points through. So one example of this could be, for example, a metal detector, right? So in airports, you have a metal detector, and you want to flag every object that contains some metal content in it, right? So if there is metal content in some object, then you want to call that label 1, right? So you don't want to let any metal go through, right, undetected. So you set the threshold to be some low value so that every possible harmful object is caught by your classifier, right? So that's one example of when you will set the threshold to something very low. Okay, so was this
one question,
question?
sir? In that, in the first diagram, W transpose X is equal to 1.38. That's the solid line or the dotted line?
The solid line. Solid line is.
And the threshold is the dotted line.
No, the threshold is the usual boundary that we are used to, right? W transpose X equal to 0. I have drawn the dotted line just to show that they are parallel.
Okay, so the threshold is W transpose W transpose X is equal to 0.
Okay. The decision boundary is W transpose X equal to 1.38, right? So the solid line is the actual decision boundary in this case.
And then what will be called W transpose X is equal to 0? Is there a term for it?
In this case, no, right? So see, in general, we have W transpose X plus B equal to 0, right? So that's the equation of the decision boundary. But in our course, we have not taken into account the bias term, right? So
okay,
right?
Okay, got it.
Yeah.
So you can. So when we say decision boundary, one question, it's whether it's plus B or minus B, it's or no B, it's W transpose. It's basically the okay, wherever W is, the vector or the whatever the plane or the vector perpendicular to that will be the decision boundary.
Yeah, so perpendicular to, so the W will be perpendicular to the boundary. That's the one boundary, thing.
Or vice versa. Okay.
Yeah, yeah, right. So one note for all of you, right? So in as far as our exam is concerned, right? Always assume that W transpose X equal to 0 is the boundary, right? So there'll be no change in that. So if you want to be very sure, we won't ask this question, okay, in the exam. So we won't ask questions where this particular question will not come, right? So the boundary will not be shifted. But in general, you can in general assume that if the threshold value is not given in logistic regression, then W transpose X equal to 0 is the boundary. Okay, I hope that is clear to all of you.
Sir, couple of quick points, sir. In the simplest form, can we say that when we are taking threshold as 0.8, so most of the points will fall in red region, means y hat equal to 0. Is that correct?
Yeah, I think that's a fair assumption to make. Yeah, you can assume that, right? So
And the reverse is for point t equal to 0.2. That most of the points will be on the right hand side, means in the green region where y hat equal to 1, right?
yeah. So yeah, one way of maybe one analogy that suddenly comes up to my mind is if you have a fishing net, right, and you have control over the fine,
Size of the net,
yeah, the granularity of the net, right? So if you have a very small granularity, then you'll end up catching everything that comes by your way, right? So that will be like a small value of t. On the other hand, if I don't know if I'm giving the analogy correctly, but something like that. Okay, so
got it, sir. And my second point was that we wrote the equation at the top that y hat equal to 1 when probability of y equal to 1 when x is greater than equal to t, right?
correct.
So I think you explained, sir. I missed that point. How it is becoming probability of y equal to 1 given x equal to t. So anyhow, whether it is equal to t or greater than t, will classify it as 1 only, right?
Here we'll classify it as 1. So the reason I'm linking this to the decision boundary is as follows, right? See, the decision boundary is that part of the surface where you can, if you just step to the other side, you will predict it as 1. If you just step to the opposite side, you will predict it as 0, right? So when will that happen? That will happen when p of y equal to 1 given x is exactly equal to t, right? Only in that case will you be in a situation where you move slightly to the left, you predict 1, move slightly to the right, you predict 0.
Yeah, anyhow, but we started with the question that if the point is exactly on the line, then we'll classify it as 1 only, right?
Yeah, that is true. That is true. If the point is on the boundary, the prediction is 1 according to convention that we follow.
Thank you, sir.
Okay, so
Excuse me, sir. Hello, sir.
Yeah.
Sir, you've told right whenever threshold is not given, we can assume that the W transpose X is 0. I just want to understand if the reverse is true. Like whenever W transpose X is equal to 0, can we take the threshold as 0.5 or it could be some other value as well?
Yeah, so this threshold business, first of all, comes only for logistic regression, right? So let's make that connection clear, okay? So
yeah, I'm asking in logistic regression here only, sir. Yeah.
So there are two cases, right? Either we will give you the threshold. When we give you the threshold, then you have to apply exactly what is given here, right? This formula.
Okay,
so
sir.
you have to use the threshold we have given. Okay.
Yes, sir.
Second case is when nothing is mentioned about the threshold. In that case, you can assume that W trans t is equal to 0.5, right? If t is not mentioned, assume that t equal to 0.5. T equal to 0.5 is what? Usual W transpose X equal to 0.
0.
Right?
Yeah, that's what. So the reverse will also be true. Like W transpose X is 0 in logistic regression. It means
you
that
can assume T to be 0.5.
threshold is 0.5.
Yeah, exactly. Yeah.
Okay, sir. Thank you. Thank you, sir.
Yeah. So are there any more confusions regarding this threshold business?
No, not confusion, sir. But as you said, sir, that W transpose X plus D, we are not considering that D part in our course.
Yeah.
But say, for example, even that D is there, sir. So whether where my this W vector will still pass through origin or will it shift?
W will still pass through origin, right? Because that's a vector, no? So
that's by definition, right?
Yeah,
by definition.
correct, by definition.
And then what about this threshold line, sir? Will it shift?
The decision boundary will not. So if B is not 0, then your decision boundary will not pass through the origin, right? So this part is actually the B. So here B is say minus 1.38 or 1.38, depending on how you call it.
Okay, sir, got it.
Okay. Can we move on now?
Yeah, sure.
Okay, so we'll now move to SVMs, right? So assume that you have a soft margin linear SP, right? So this is the case where the data is not necessarily separable, right? Linearly separable, but still you can have a hyperplane that separates most of the points decently, right? So this is the case. So what is the hinge loss? You have been given this data set here. You have to compute the hinge loss. So what?
Sir, sorry to interrupt. Just
Yeah.
one question on threshold, sir.
Yeah.
Will there be any chances that the threshold can be equal to 1? Like,
So
will there be any scenarios? Will it be equal to 1? Because natural logarithm of 1 by t minus, if you go by that formula, it is going to be infinity, right? So
correct. Yeah. Good
that's
point.
one.
So that will never happen, right? So if your threshold t is 1, you will with this sigmoid function, when will the threshold, when will this be equal to 1? When will the sigmoid function be equal to 1?
Sorry, sir. I
So
truly don't know. So that's why I'm asking that
okay,
question.
so the sigmoid function will never be equal to 1, right? Because it's strictly between 0 and 1. It will tend to 1 when the data point x is so far away from your decision boundary that it's
Okay, so we are going by the graph you are telling. That is, it never touches 1 and it never touches 0. Am I right, sir?
Yeah, that's the two lines at the top and bottom are
Yeah.
asymptotic, right? So
it will never go to 1.
it will never go to 1. So you will never set the threshold to be 1.
Okay, sir. Okay. Got it, sir. Thank you. Thank you, sir.
Yeah. Okay, so soft margin linear SPM, right? So this is what we have. Now, can someone tell me what is the hinge loss that we use in SPM?
That was for like each data point, that was the maximum of either 0 or 1 minus W transpose Xi Yi.
Yeah,
and then we add up all for all of it, and then we get the total loss, I guess.
Yeah, right. So that is the hinge loss. So it is summation 1 to n, either 0 or 1 minus W transpose Xi Yi, right? So whichever of these two is the maximum, you just replace that with this expression and you just sum it across all the n data points. So it's a very quick computational exercise. So let's go ahead and do it. I have just replaced this table here with this one. Now, can someone just fill in these values? What is it going to be? First row, the values for the first row.
First will be 0.
Okay, it will be 0, 0.
Second will be 0 again.
Okay.
Third will again be 0.
Not really.
Is it -1, yeah? -1.
No, -1, between -1 and okay, yeah, loss is 0. Yeah. Sorry.
Right. So that's right. Okay. Fourth row.
It's again -1, I guess.
No, 1 loss will be 1.
Is it?
X means x1 and x2, na?
Yeah.
Yes,
Correct.
yes.
So is this correct or wrong? I have written 3, 3. Is that correct or wrong?
I think it's correct. Actually, it's 1 plus 2. So yeah, it's 3.
Right. So let's just do this part alone. So W transpose X is what? W is 0. So 0 into 0 plus 2 into 1, right? So W transpose X is going to be 2 into Y, right? That is -1. So W transpose X Y will be -2. Okay, so 1 minus -2, you get 3, and max of 3 comma 0 is 3. Right? That's how we get this. What about the next row?
0 and 3.
Okay, 0. I'm getting 0, 0. Is that correct?
Yes, sir.
Loss will accumulate, right? Okay, you are not doing the accumulation. Okay.
You will submit the loss at the end now.
Okay.
Yeah. Right. What about the next one?
Next one, loss will be 0 again.
Okay, this is -1 and 0. Final one?
Final one is 0. So again the 0, I think.
1, I think. 1. It should be 1.
Okay, right. It is 1. So W transpose X is what? 0. This term see you can practically ignore the first feature, right? Because first weight is 0. So you just need to look at W transpose X will just be X2, in fact, right? So X2 is 0. And so since X2 is 0, all that you need to worry about is this 1 here, right? So
So the
1 minus this is
last one will be 1 1 or 0 0, sir? Because 0 into minus 2 0, then 1 into 0 0.
yeah. So this is 0, right? 1 minus 0.
If my W transpose X is 0, so W transpose X into Y, that will also be 0, no, sir?
And then
1
it will
is that, right?
subtract to 1.
Yes, sorry, sorry.
Okay, so did everyone get what we have done? It's very simple algebra. So
Yes, sir, we get it.
okay, so there is this one way of doing it. There is another way of doing it. Okay, so what could be the other way of solving this? Is this the only possible way of solving this problem?
Is it plotting the points and carrying
Yeah.
Zaya?
Right, geometry. So this is how the geometric way of doing it will look like. So you plot 0 1, W is 0 1, right? So 0 1, you plot the weight vector, and then you plot the separating hyperplanes, right? What are the rather the supporting hyperplanes? What are the equations of the supporting hyperplanes?
So W transpose X is equal to plus gamma and minus gamma.
W transpose X is +1 in this case and -1. These are the two.
Right?
Yeah, the generalized form is gamma. But sir, do we always normalize gamma?
Yeah, we always do, right? So we always do. So it's always W transpose X equal to plus or minus 1. Okay.
So sir, if it's not normal, so sir, would there a normal scenario would be W transpose X is equal to plus gamma and minus gamma, and then we normalize gamma, and then we say that because the left side is also integers, it won't matter if I divide it because the supporting plane remains the same.
Yeah, so this W and gamma you can like normalize together, right? So
yeah, sir, got it.
Yeah,
Got it, sir.
So W transpose X equal to 1 will be what? 0 1, right? So it will be X2 equal to 1.
Sorry, sir. So if I just can answer, so W transpose X is equal to plus minus 1 will always be the hyperplanes geometrically.
Yes, yeah. So of course, because of the way we have chosen a W, and the way we have set up our constraints, right? So it will always, the supporting hyperplanes will always be W transpose X equal to plus or minus 1. Again, because of the way we have chosen W and the way we have defined the margin. The margin is 1 by norm W, right? According to our...
Yeah, so gamma is 1 by norm W. So
D is 1 by norm W, right? So the margin is 1 by norm W. We are maximizing that, and we have chosen the nearest points to lie on W transpose X equal to plus or minus 1.
Okay, so I'm still not very 100%. Okay, go ahead, sir.
Yeah, we'll come back to that. So there's a problem where we'll discuss this also. Okay, so for now let's stick to W transpose X equal to plus or minus 1. So that will give you what? X2 equal to 1, X2 equal to minus 1, right? You draw these two. So first you draw W, then you draw the supporting hyperplanes. Okay, and then you plot the points, right? So if you plot the points, you will see that this is how it looks. Now, can you tell me which of these points are violating the margin?
Just 1 point, 0 2.
2 point.
Sorry, no.
There should be 2 points.
Minus
1
2,
on
0.
the decision boundary, and both are red. Actually.
Yeah.
Minus 2 0 and the other one, which is 2.
Which is the other one? Minus 2 0. So this minus 2 0 is violating the margin,
0 2
right?
and 0 2.
Yes.
0 2
and then 0 2.
Okay.
Yeah.
How do we? I'm sorry. I actually shouldn't have drawn this line. This line is wrong. So see, the first hinge loss is what? This 0 2. For the 0 2 example, the loss is nothing but this distance, right? So it's the distance from
I think the 0 2 1 is the top one, right? In the green segment.
Yeah. So
Yes, that is 0, 2.
Sir, in the loss column, only 2 points have loss. Other
correct. Yeah,
zero loss.
that's right. So it is 0, 2 corresponding to say 0, 2, which has a loss of 3, and minus 2, 0, right? Which has a loss of 1. So what I'm saying is this distance from the dotted line is the loss, right? So here the distance is 1, okay? Here the distance is 3. So 2 units till the decision boundary and 1 unit to the correct side. So the total distance is 3, or 2 minus minus 1, right? You can also look at it as 2 minus minus 1. So that is 3. Ignore this line here. That's a wrong one. Okay, so did everyone get how to do this geometrically?
Could you explain the last portion once again? I lost it somewhere on the point where we found the 2 red points which are causing the hinge loss. Could you explain after that point?
Okay, so these 2 points are causing the hinge
Yes,
loss,
sir.
right?
Yes, sir. That I understood.
So the hinge loss is what? The geometric interpretation of the hinge loss is the distance of the offending point from the correct side of the hyperplane to which it should actually belong. So recall that sir calls this the bribe, right? How much bribe should I pay?
Right, so got it.
So that it should be pushed
So
in.
then the point on the decision boundary has to travel the equivalent of 1 unit.
1 unit, correct.
And the other one has to travel 3 units to get onto the decision boundary where it will make an impact. Right,
Yeah.
so got it. Thank you.
But sir, for geometrically, let us talk about the second point, 0, 2, right? So
No,
say for example, if it is not coming on the hyperplane on the -1 side, it is in between 0 to -1. Then also we had discussed that it will be rightly classified. It will be classified as red only, right? So why I'm taking the loss as 3 point here? I can say that the loss is 2 points only. Right?
No, your condition is it should be not just classify. It should not just be classified correctly. It should also be classified with a margin of 1, right?
Okay. Okay, fine.
Right. That is
so total loss is 4 units. Huh?
3 units, right? Oh yeah, 4 units. Yeah, correct. Total loss is 4 units.
And sir, one more
So we
question.
have to sum it up, right?
Yeah, the total loss is. Okay, I'm hearing an echo. Yeah, you should sum it up.
Hello, sir. Sir,
Yeah.
the distance between the hyperplanes, what's the formula? Is it 2 by mod of w square?
We'll come to that, right? It's the distance between the supporting hyperplanes is 2 by norm w. 2 by norm w.
So is it a 2 by norm w square?
No, right? It's not w square. It's actually 2 by norm w.
Okay.
We'll come to that, right? We'll come to that. There's a question on that where I'll explain this part.
Sir, here. Hello.
Go on. Hello. Yeah. So someone was asking, Sarvesh, or someone was asking a question, right?
Hello. Am I audible?
Yeah.
Yeah. Sorry. So the distance between the decision boundary and the supporting hyperplane here is 1.
No.
So,
it's 1 by norm w, right?
So does that mean norm of w is 1?
Correct. In this case, it so happens that norm of w is 1. See, when I again we loosely use these terms, right? Distance. When we say distance, we are not actually talking about the exact distance, right? We are talking about some kind of scaled distance, right?
Right.
So here, both are the same. As you said, the norm w is equal to 1. Therefore, the distance and the scale distance, whatever we call it, both are the same. Okay, is that fine?
Yes, sir.
Okay. So,
Hello, sir.
Yeah.
Sir, actually, the support vectors, no? I mean, the first support vector is on 1, that is the green line. And doesn't the second support vector should be on the red point, which is on axis, 0 axis, sir? I mean, generally, the support vector takes the point, the red point, and the green points. I mean,
okay. So,
right around.
Hold on to this question. We have 2 questions on what are the support vectors. There, it will be more appropriate to discuss. Okay. So, I'm not. It may look that I'm avoiding a lot of questions, but there is a place where we'll be discussing all this.
Okay, sir. Okay, thank you, sir.
Yeah. Any other questions regarding the hinge laws?
Yes, yes, I have this one question. Here, when we are looking at the bribe, it's always the perpendicular distance, yeah?
Perpendicular distance, distance perpendicular to the supporting hyperplane, right? So from the
Yes.
point to the supporting hyperplane.
Okay, thank you.
Okay, so we are moving on. Now we'll move to PCA, right? So we are going to move to PCA of week 1. So you are given a matrix here. So is this a valid covariance matrix?
Which one, sir?
It should be a
No, it's not.
symmetric
No,
matrix,
it
no,
is
sir.
It's
not
not.
symmetric.
Okay,
It
right?
should be a
That's correct.
symmetric.
So I'll just quickly go over a few ideas from PCA in case some of you have forgotten this. So what is the formula for the covariance matrix for a general data set of endpoints?
1 by n XX transpose.
Okay, 1 by n XX transpose. I'll just start with the more data, the vector version of it, right? So it's 1 by n sigma xi transpose. So is this always correct for any data set?
No, it
This
depends
is a
on X.
centered
X.
data set only.
Correct, right? It should be centered. So if not, it's xi minus mu into xi minus mu transpose, right? If for a centered data set, mu is 0. So this is sigma xi transpose by n. Okay, so that is the covariance matrix. Now we want to find C transpose. So you just take the transpose and flip the items, right, in the product. So it will turn out to be C itself, right? So this is a short recent proof for why the covariance matrix has to be symmetric. Of course, you can write this as XX transpose by n. That's the simpler way of writing it. Okay, so for this example, the covariance matrix is not symmetric, so you can directly, this matrix is not symmetric, therefore it cannot be a covariance matrix. Okay, so that is one part. Now let's look at another case, right? Is this a valid covariance matrix?
Looks correct.
No.
No.
But
Why
we have to
why?
check the orthonormality.
So again, the symmetric.
Okay, it's
I
symmetric,
guess
right?
it's symmetric, but the variance
It
can
is
be 0, right?
symmetric,
So the
but sir,
diagonal
we'll have
entries
to.
is the
I think
variance.
this does not
Sir, we'll
support
have to
the
check for
orthogonality.
the positivity, right? The positive definite.
Semi-definite, semi to
Yeah.
positive definite.
Okay, how will you check for positive semi-definiteness?
All the lambda value should be greater than equal to 0.
Okay, that's good. How will you compute the lambda values?
Okay, that's
First we will take 2 by 2, then we will take 3 by 3 and determinants.
We could use the product of lambda equals the determinant of C and sum of lambda
And sum
equals
of
T.
lambdas is a trace.
Okay, that's one way. Now, is there any other way that you are taught in MLF long time back for those who have done it last term?
You can just calculate the eigenvalues and eigenvectors directly.
Okay, how will you calculate the eigenvalues?
We'll have to calculate that a minus lambda into I is equal to 0.
Okay,
From
right. So
that
we'll
we'll
do that.
get.
That's good. We'll do that.
Some
But
characteristics equals
can we just take any vector in that vector space and just do v into a into v transpose, and that if that's greater than 0, then we know it's semi-definite. Just take any vector. Is that also a possibility? Let me just check that. You go ahead, sir. I'll just check that.
Okay. Right. So we'll do this. So this is C. C is 1 0 1 0 1 0 1 0 0. Right, and you do minus lambda I. So this is what you get. Now, if someone is interested, please work it out right now and tell me what it is. Right, very quickly you can work it out. And can you tell me what lambdas turn out to be?
Is equals to 1, sir?
There is one lambda which is 1. What about the other lambdas?
0 plus or minus 1.
Okay.
Am I right, sir?
You'll have to work it out, right? So let's go through the steps one by one, right? So just algebra, but anyway, let's do that. So 1 minus lambda into 1 minus lambda into minus lambda, right? That is what you will get.
Yeah.
And then you will this term is 0. So if you expand it along the first row, you'll finally end up with 1 into minus 1 minus lambda. So is this correct? First, can someone tell me if this is the correct expression for the determinant?
Yes, sir.
Yes, correct.
Okay, so what can we do now? We can take 1 minus lambda common or minus 1 minus lambda. Is the second expression correct? I just want someone to tell me if it's right, then we'll move on.
Yes, it's correct, sir.
Okay, so now what happens? Is this correct? Is this step also correct?
Yes, sir.
Okay, so now you get these 3 lambdas. Now from this, can you conclude one way or the other?
Lambda 3 is less than 0.
Yeah, right. So lambda 3 is less than 0.
So
And
it is not positive semi-definite.
Yeah, right. So you have a problem. So now, why should it be positive semi-definite? One way is to see through the linear algebra, but is there any other way to? What are these lambdas for a valid covariance matrix?
I think somehow it is related to variance, and variance is always a positive number.
Correct, right? So that's the way to remember this. In
Somehow,
case, yeah,
I
that's
don't
the way
remember
to.
I don't remember the formula, but somehow I remember this statement which Professor
Yeah,
has
yeah.
said.
Correct, right? So this is what Sarah said, and this is the easiest way to remember in case you are not able to remember the linear algebra concepts of why this is PSD and all that. Always remember that the lambdas of the covariance matrix are the variances along the principal components, right? So they should always be non-negative. Okay, so they can be 0, by the way. You can have 0 as the
Yeah, that's why it's positive semi-definite. No,
right.
that's why it's positive
Yeah.
semi-definite.
Okay, so there's one more related question.
There's one more rule to do with positive semi-definite, but it wouldn't have helped us here.
Unnecessary ना इतना बड़ा चक्कर लगेगा.
Okay, so there are like lot of noise.
There's a lot of background noise there.
Yeah, can all of you please mute? If you want to ask a question, please unmute. Otherwise, request to all of you to mute. So there's a related question that I wanted to ask, but I'll skip it for now. You can you don't need to answer now, but you can come back later. Is every positive semi-definite matrix a covariance matrix for some data set?
No, right? Because some of them are not going to be symmetric.
Yeah. No, right? So by definition, you have positive semi-definite. We have symmetric PSD matrix, right? So the symmetry comes with the positive semi-definiteness, right? So assume that now.
Right.
Yeah. Now, can you tell me what you think of this? Is every symmetric PSD matrix the covariance matrix of some data set? So what we have here is, if a matrix is a covariance matrix of some data set, then it has to be positive semi-definite. That's what we have seen, right? Now I'm asking the other way around. If some matrix is symmetric positive semi-definite, should this be a covariance matrix of some data set? Can you show that?
Answer is yes. I don't know how to show
Yes,
it.
sir. It should be.
It should be, because I can always create a data set
based
on those variances.
Right. So here is a very, very quick proof for that. This is again not from the exam point of view. So if a matrix is symmetric positive semi-definite, right? So A is such a matrix, then you can do this eigen decomposition, right? If you will recall, this is a symmetric matrix, so you can do Q D Q transpose. Okay, D is nothing but the diagonal elements will have the eigenvalues, and they'll all be non-negative. So I can always write D as the square root of D into square root of D. Right, so because these elements are all positive or 0 at the very best, you can split it like this, and then you can see that this nicely factors into the form B into B transpose, right? QD our half is B, the other one is B transpose. Now compare this with X into X transpose. Right, if you choose X to be B or 1 by N into B or whatever, right? So you can, that's a constant, so that doesn't matter. You can always find a data set for which A is the covariance matrix. Yeah, of course, this is extra, right? You don't need to worry about this now. We'll come back to this later.
Sir, just a quick clarification. This
Yeah.
singular vector decomposition and eigenvector decomposition, both are same? Or I don't want to discuss. I just
Okay, they are not the same.
What is the question? Sorry, I couldn't get that.
Is SVD, singular vector decomposition and eigen decomposition, do they mean same thing?
No.
They are not the
Okay,
same, but
they are
eigen
not.
decomposition is used in
SVD.
the derivation of SVD. Right?
Okay, I will figure it out, sir.
Yeah. So we have.
Sir, excuse me, just one last question.
Yeah.
The fact that if a matrix is positive semi-definite, then it is symmetric as well. This was something we assumed for the last question, or is it
No,
always the case?
We always, so see, we by definition we define positive semi-definiteness only for symmetric matrices, right? So we say a symmetric.
All right, got it. Yes, sir, got it.
Yeah. Okay.
Got it. Thank you.
Okay. So one more question on PCA before we move on to other subjects or other topics in this course, right? So
I'm sorry, if I can take you a little back.
Yeah.
When we were talking about that eigenvalues being non-negative, that was important for it to be a covariance matrix. You mentioned something about variances. I'm sorry, I didn't catch that.
See, variances, the eigenvalues of the covariance matrix are the variances along each of these principal components, right? So for example, the variance along the first principal component will be the largest eigenvalue.
Yes.
Right. So since the variances cannot be negative, the eigenvalues of a covariance matrix cannot be negative. Okay, that is the link. I mean, that's one way of seeing why the covariance matrix should be positive semi-definite. Or should have non-negative eigenvalues.
No, but you were saying what if you don't want to solve for lambdas.
Sorry, I didn't get that.
If we don't want to solve for these lambdas with this, algebraic method, is there a shortcut for that?
I'm afraid we don't, right? At least to my knowledge, we don't have.
Just to interrupt, I mean, on a related note, if we can just write it in the quadratic form or in the polynomial form, the characteristic equation, we can use Descartes' rule of sign, right? To find out how many positive roots are there and how many negative roots are there. So if there is a negative root, we can say that this is not positive definite.
You mean expanding this characteristic polynomial? Or?
Yeah. So basically expanding that, and we'll get the polynomial, right? So, and then we can use Descartes' rule of sign. So just we just see how many times the variable changes its sign, and from there we can say.
Okay. I'm like, yeah, that's like very. I don't even remember that. Maybe someone else can.
Yeah. So basically, this is what we have this is what we have learned at my other college. So if so if anyone is interested, they can look up Descartes' rule of sign. That is a really easy way. So I generally use this in this type of questions, and I get the right answer.
I'm sorry, I'm not able to catch the name. Could you just put it in messages?
Descartes. Okay, I'll just DESCRTS. Okay, I'll just put it in the message.
Descartes what? Descartes what?
Rule of signs.
Rule of signs.
Rule of signs. Yeah.
Okay, thanks for that. So
thank you.
And yeah, we'll move on now. So see, you are given a data set, right? X is a data set. How many features does it have?
Two.
So two features.
Two, right? So 2 features, 8 data points, right? So that's the data set. Now you have to find the principal components. So how will you go about it?
Sir, by looking the data set, it looks like it have 2 principal component, 1, 1 and 1, -1.
Okay, interesting. We'll come to that. So you are like almost, you are fairly correct. At least you are not incorrect.
The eigenvector is actually the finding the principal component, no?
Yes. Yeah. You have to find the eigenvectors of what?
The covariance matrix.
Yeah, right. So we have to first calculate it. No? So we'll do that. So 1/n into XX transpose. So you have X, you have X transpose, right? You just plug it in here. Now this turns out to be a very simple computation. So can each one of you do one of the 4 entries of the covariance matrix? and tell me what the 4 entries are. You can do parallel computation here since there are enough number of people in the call.
Eight, 16, and I think it'll all be 96, 96, 96.
Sir, A11 is okay.
96, 96, 90,
Sir,
96,
80.
96.
So it is 80.
Yes,
A11.
80. 80.
Okay, are you forgetting to divide by something?
So it is
Yeah,
okay.
so I have to divide
it
by
is,
8.
It is,
So
Okay, C11 is what?
10.
Okay, C12. So if C11, okay, what is C12? What is C21? Did anyone come get to that? You tell
Sir,
me C.
okay.
that's what I'm saying, sir. All the values are the same.
No, all the values are not exactly same.
The centering is not required here.
You tell me, right? Yeah, I forgot that. So you should be center it or not? I mean, of course, we have to center it, but
There is no need in this case.
yeah, why is that?
The mean is 0, 0.
All are
Yeah,
okay.
it's already centered. So what is if one off diagonal element? If you tell me other one is the same, so what is it? It's not too hard. If you look at the pattern, you will see.
It's 12, 12, 12, 12 is also, no?
So 10.
10 is the diagonal entry, but what is the off diagonal entry?
5.
0, sir. 0, 0,
sir.
0, 0.
Okay, that's correct, right? They are 0, 0. So if you look at it, you will notice, right? So the sign of these 4 numbers is just the opposite of the sign of the first 4 numbers. Okay, at least here. So anyway, so it's just algebra, right? I don't want to spend more time. So you will end up getting a covariance matrix like this: 10, 0, 0, 10. Okay, so this is just computation, right? You can figure it out later. It's nothing hard. Now, what are the principal components for this setup? One answer I got earlier was 1, 1 and minus 1, 1. Is that correct?
We have to normalize it.
Yeah, this is a diagonal matrix, right, sir? The eigenvectors are the diagonal entries.
Yeah, eigenvalues are the diagonal entries. So 10 are the eigenvalues. What are the eigenvectors?
So
1001.
Okay, I got one more answer. Someone told me 1 minus 1 1 minus 1 1. Another answer is 1001. Anyone else? Okay, I'll give one answer from my side. I'm saying that this is a principal. These are the principal components. Am I right?
How you calculate this?
Okay, good question. So we'll plot these.
They can be principal components. Yes.
Yeah. Okay, so this is the plot, right? So this is, if you look at it, it's 2 2 minus 2 minus 2 4 4 minus 4 minus 4, right? I've just plotted these points. Now, how will these two principal components look like if I plot them on this graph?
So there'll be one will go through 1 1 or whatever, some scaled version of like y is equal to x and y is equal to minus x.
Okay, right. So it look like this, right? They'll go through these two. Will go through these 2 points. Now, is this the correct answer? Or is this the only answer?
To normalize it, right?
This is already normalized.
Yeah, so the norm W1 is 1,
Norm
right?
is 1.
So norm W2 is 1 and they are perpendicular as expected. So it all works out fine. Now, is this the only answer possible?
Sir, 1 1 we can make -1 also, right? And -1 1 we can make it 1 -1 also, right?
Correct. We can do that, right? We have one more answer. So
Sir, from the covariance matrix, I have to calculate A minus lambda I, mean actually C minus lambda I, the characteristics equation. After that, we can found the lambda.
lambda here is easy, right? The for a diagonal matrix, the eigenvalues are the diagonal eigenvalues, right? So the 10 and 10 are the lambda 1 and lambda 2 in this case. Okay, now the question is about the eigenvectors. So what is an eigenvector here? Okay, do you see that every vector in this space is an eigenvector? See, what is this matrix?
It's a rank 2 matrix, right? So like it's a full
Yeah,
rank.
full rank matrix. All the vectors
So
would
all
be
the
eigenvectors.
So what is C? C is actually what? 10 times the identity matrix, right?
Yeah.
Yes.
So C into X is equal to 10 into I into X, right? So that is just 10X. So every vector in this plane, in this space, is an eigenvector with eigenvalue 10.
Right.
Right. So this is the case where your data is initially uncorrelated. Okay, so there are off diagonal elements are 0. So the W1 and W2 are the X1 and X2 already represent principal components, but it's more special in the sense that every possible pair of orthogonal directions are principal components. Right? You can change your basis whichever way you want. You will. So the variance along all these directions is going to be the same. Okay, there's
So
no.
if we actually derive the eigenvectors, we will get it as some value of some parameter t or something like that. Then there's an infinite set.
Right. Yeah.
You'll have to. If you had done that, you would have spotted it easily.
Yeah. Right. So this is also a correct pair. Okay. So by the way,
here because the eigenvalues are repeated. That's why like the number of times the eigenvalues get repeated, that space correspond to the dimensionality of that space correspond to the eigenspace, right? Like in this case, 2 times the eigenvalues get repeated, 10 and 10. So we have like a 2D space of eigenvectors, which is the
yeah.
plane.
The eigenspace for the eigenvalue 10 is R2 itself.
Yes.
Yeah. So can
how
we?
do we derive that W1 and W2?
So how do we get?
So the reason is one more thing. See, if you take C minus lambda I, right? You have to basically to find the eigenvectors, you have to find the null space of C minus lambda I, correct? Now
Yeah.
C minus lambda I is a zero matrix. Right? Which means basically that takes every vector to the zero vector, right? So anything in that, everything is in that null space essentially.
Yeah, that's the eigenspace, right? Eigenspace of 10.
Correct. So correct. So every set of orthogonal vectors in this space will be basically principal components.
Right.
Okay. That's one. Okay. I can relate to that thought.
Okay, so yeah, this is like too much of maybe linear algebra in the first half of the session. So I'm sorry for that.
Just one thing.
Yeah.
You got W1 and W2 are basically eigenvectors, right?
Correct. Yeah.
So then we can. Okay, got it. The rest can be stored. Got it, sir. Thank you. Please continue.
Yeah. So we'll now move on to regression, right? So now it's our turn to look at regression.
One thing, how did we calculate it? If it is the points are different in general, how do we calculate? Is it C
So-
minus lambda only?
Yeah. So you do C minus lambda into some W equal to 0, like say W1. So you find out what W1 and W2 are individual, right? By solving the eigenvector equation, you'll have to.
Okay, the regular usual
The usual
procedure.
method. Yeah.
So for this, the
Hi.
eigenvalues are 1 minus 1 upon 10 now, I think.
For which one?
This covariance matrix for question 4.
Yeah, question 4. Can you tell me
Yeah, sir.
again?
Sir, eigenvalue of this covariance matrix.
10 and 10, right? There are like two. There is one eigenvalue which is repeated twice, so that's 10.
Okay,
It
10
is 10.
is that.
Yeah. So for a,
Excuse me.
yeah.
Yeah, so basically this question just came to my mind. This was in quiz 2 that we had to find the rank 1 approximation of a point. Is that just the approximation of a point along the first principal component?
It's the singular value, right? You are looking at the first singular vector and singular value. You are talking about MLF quiz question, right?
Oh.
Sir, in
Oh, okay, sorry.
Sir, in
Yeah.
MLF first, they have learned that first calculate lambda value, then put it in the characteristics equation, and then x1, x2 calculate the uh, using the from the equation calculate x1 and x2. This is our
That's
eigenvalue.
the procedure, right? Yeah. So see, we won't ask you. You don't need to if you have done MLF, right? Like last term, we won't ask you to compute eigenvector and not, right? So don't wait. So I mean, at least we won't ask you to compute eigenvectors using the method that you learned in MLF, where you solve a system of equations. All that is too much algebra, and the
Yes,
course
same
is not about algebra.
follow here, no?
Yeah, you can follow the same thing, but you don't need to worry about, you don't need to go back and learn how to compute eigenvectors, because that's not the aim of this course, right? So this is just to give you just to give you an example of what can be done. That's all.
Sir, one more thing, sir. Sir, eigenvalue we calculated using lambda a lambda minus I or lambda a minus I.
Mm-hmm.
A here is the covariance matrix, okay?
Yeah, okay.
And we take the determinant of that covariance I mean to say a determinant of a lambda minus I and equate it to 0.
Yeah, lambda I minus a, and you take the determinant equated to 0. Yeah.
Yeah. The lambda I minus
A minus lambda I will be.
a minus lambda I, no?
Both are the same, right? So yeah,
from there you will get values of lambda, so those will be your eigenvalues.
Sir, can you please solve it for the sake of completion,
Okay.
sir? I mean, many people are asking this doubt, I think so.
For this problem?
Yeah, for finding W1, and I think this is what we are trying to find out, right?
No, see, no. So here it's very simple, right? So you don't need to, so okay, maybe I'll do this, but here, see, what is A here? Your C is basically 10 times the identity matrix, right? That's correct. So 10 times the identity matrix. So what is C times X? Consider X to be any vector, right? C times X is what? 10 times I times X, which is just 10 times X, right? So Cx equal to 10 times X. So any vector X you take, it will be an eigenvector. That is all we need to do here.
Got it, sir. Got it. Yeah.
Right. So.
Sir, usually first principal component has the highest variance. Here there are two lambdas and they're both equal. So none of them is first or second in terms of rank, right?
Yeah, you can, both are like equal in terms of importance.
And how do we decide how many principal components you should have in this case?
This is like a very highly impractical situation, right? So where a real world data set will never fall into this kind of, you'll never encounter something where every single direction is important as the other direction, right? So so this question perhaps doesn't arise.
Okay.
So just to answer that question, can we draw similarity what we had learned, that we have to consider all the lambda values till the time we are covering 95% of the variance.
Right. That heuristic stays. Yeah, you can.
Yeah, from that point of view, I think she was asking.
Okay.
How many principal components can we take?
Got it. Then in this case, you'll have to take both, right? Because if you take only one, you'll get only 50%.
50%.
Here both are giving 100%. So this is purely curated data. So.
Yeah. This is like a dummy data. So.
Yeah.
And so here the answer is find the principal component. That is, they are asking number of principal components or the value of the principal components.
The
number, but let's ignore it for this question, no? Because here it's like it's not a good example question to discuss that particular aspect of PCA.
Yeah,
right?
it's an unusual question.
Yeah.
Sir, will you take a small doubt on PCA at this point of time? You had said that while addressing the problem.
Okay, depends on how big it is,
No,
right?
it's very small, sir. It will not take more than 1 minute, sir.
Okay, yeah.
Yeah, this is related to PCA line, sir. You know, in a very layman, I'm talking in a very simplest manner. We started with representation learning, right?
Yeah.
Like where we projected data in a compressed form. So in PCA, what we are saying that we are taking a line, correct? And we are projecting all the data points on that line, right? And then there will be error, that those perpendicular lines will be error. So again we are projecting them on other line, right, which is perpendicular to my first line, correct?
Right.
And then again there will be error. In this way I keep projecting line, right, till the time error becomes zero, or we can say that 95% of the variance is getting captured, right? So when we talk about the final PCA line, so what is meant by final PCA line? Actually, it is a combination of all the principal components, na?
Yeah. So if you're looking at reconstructing the data set, you'll have to use all the k rounds, right? Depending on which k you want to stop at, you'll have to use all the k rounds to come up with the final reconstruction.
Right. So why do we call it a PCA line? It's not a one line. So it's a combination of so many principal components, right? And all of them are perpendicular to each other.
Yeah. So each one is still a line, right? W1 to WK, each of them is a line in RD, right?
Correct. So, but what will whether the final K which we got, so that will be a final PCA line, or the first one which is capturing the maximum variance will be the PCA line, sir?
No, all of them are PCA lines. They are all, each one is a principal component.
Got it, Basu, but you are using the plural form. You are saying the PCA lines, but in video or in normal discussion, we generally say PCA line, the PCA line, the PCA line. So that makes me confused.
No, that I mean, okay. I don't know where that is, but that's just very rough usage. PCA, there are, if you choose K principal components, then there are
that concept
K.
is clear till the time we are capturing 95 or more than that, or even may
There are
happen.
k lines, right? So that is k lines. Yeah.
Okay, got it, sir. Thank you.
Right?
This was the only doubt.
Yeah. Right. So let's move on to regression now. So you have a data set D, right? And D is given as follows. So there are n data points. Y1 to yn are the labels, right? No change there. But for the data points, what you're doing is you can think of this as measuring. You're doing some measurement, right? Some physics experiment, let's say, and you're taking. What do you do in a physics experiment? Typically, you'll take measurements at regular intervals, right? So you're measuring some y versus x, right? You'll take it at say 5 units, then 10 units, then 15 units, and so on, right? So I've tried to simulate that situation, but in RD, right? So you're measuring at C1 times U, C2 times U, and so on till Cn times U. Okay, and these are the measurements that you get. So these are all extra data, right? That is given to you. U is some vector in RD, and U is non-zero, and Ci is non-zero for some I. All these are extra information given to you. So is this. Okay, so is this fact that CIYI sums to 20 and CI square sums to 100. All these are part of the question. Now, you have to fit a linear regression model for this data set, and you have to find the predicted value for this test data point. Okay, so is the question clear to all of you what we have?
No, can you please repeat?
Okay, so you have a data set, right? So you have a data set, and let me share this tab. So the data set is like this. So you have typically, how does a regression data set look like? It will be x1, y1, dot, x and yn, right? This is how a regression data set will look like. Now, what I'm saying here is that each data point, instead of calling it some x1, I'm measuring it in a specific sense. I'm calling this C1 times U. And the nth data point likewise is Cn times U. Okay. You can think of this as measurement at regular intervals. For example, C1 could be 1, C2 could be 2, so on. So you're measuring something at U, 2U, 3U, 4U, so on. Okay, this is the data set that you have. how you have to fit a linear regression model. Forget about everything else. For this data set, how will you fit a linear regression model? That's the question.
Sir, sorry to interrupt. It is a bit off-topic question. Which application you are using to write this mathematical notation?
Okay, it's called matcha.io.
Maths, the spelling?
Math.
M-A-T-H, matcha, C-H-A.
Okay, thank you.
Yeah. Okay, cha for chai. Right. So yeah. So did everyone get the question now? It's just regression, plain old regression, but then the data points that are given to you have a structure, a nice structure there.
Got it.
Okay, now how will we approach a problem like this?
Maybe we can set a. I mean, we can just derive the regression line without the u, and since all of them are scaled at the end, so let's say we'll fit a regression line for c1 y1 cn yn, and the line that we get will put 5 in there. So whatever that comes out is going to be the, I guess, the answer.
Okay, as an intuition, I get it. That's correct. But u is a vector, right? You have to remember that. So we are not fitting a scalar. We are not solving a single dimensional problem, right? It's a y as a feature, y as a dependent variable depends on d features, right?
So if we start from the loss function and try and expand and see where we end up.
Yeah, that's good, right? That's the approach. So always remember, whenever you encounter something that is non-standard, right, that is different from your textbook example of applying XX transpose inverse XY, you have to use first principles, right? There is first principles will always make sure that you arrive at the correct answer, right? So this is the loss function, right? For W transpose X is the model, Y equal to W transpose X. This is the error, sum of squared errors, right? So what is the next step for regression?
Take derivative.
Gradient. Yeah.
Okay, so we'll do that quickly. So this is simple, right? You have seen this several times. 2 times W transpose Xi minus Ya into Xi. You have taken the gradient. Now gradient is, I'm just replacing Xi here, right? Xi is what? Ci times U. Okay, so Ci is a constant, so you can step outside. And Xi outside the bracket, right? That is also Ci times U. So I'm bringing the Ci inside. So is everyone okay with this step?
Sorry, please explain this once again.
So is the gradient clear?
Yes, sir. Yes, sir. Yes, sir.
Now you're plugging in Xi as Ci times U, right?
Right, sir.
Now this becomes W transpose Ci
Right, sir.
Okay, Ci is a scalar, so I'm putting it outside. So it becomes W transpose U into Ci.
Right, sir.
Now Xi is what? Again Ci times U. So I am bringing that Ci into the bracket. So it becomes W transpose U Ci square.
All right, got it.
Okay, did everyone get this part?
Yeah.
Okay, now
Yes, yeah.
Yes, sir.
what we are going to do is we are going to separate these two. I mean, we are going to set this to 0, and now something interesting is going to happen. Now you have to look at the data that is given to you. So you'll see Ci Ya here. You are seeing Ci square here. What can you do now?
Substitute.
Just is a constant. I can just pull it out.
Yeah,
We know the summation values.
WTU, W transpose TU into 100 minus 20 U is equal to 0.
Okay, so what will that give us? W transpose U will be what?
Is equal to 20 U. No, is equal to 1 by 5 U.
Correct. That's correct, right? So we have to find W transpose U, right? That nicely factors out. Now, this is the expression. Do you all agree?
1 by 5 U. Yeah, 0.2 U. Yeah.
Okay, did everyone get this step? Is there anyone who's
You
having...
will also be there, no, sir. You will also be there, no?
Good question. So where did the U disappear?
No, because the whole thing is equal to 0, right? Either U can be 0 or this can be 0.
Yeah, everything equal to 0. Yeah.
Yeah, you can't be 0.
Correct.
You can't be 0, yes.
Right. So see, that's another interesting point that you have to understand. Whenever you are given these extra conditions in questions, right? Every one of these conditions is given for a reason. So, for example, u not equal to 0 is given for that very reason, right? Otherwise, you can't set this to 0. Why is this ci not equal to 0 given, right? What is the use of that condition?
Otherwise, the summations
There's the
would
whole
end up being
summation zero
0.
becomes zero, yeah.
Right? Yeah. So at least for one I, ci should not be 0, right? So that ensures that the sum here in the denominator makes sense. So you end up with W transpose U equal to 0.2. Okay, now can you find what W is? Do you need to find W for this
No,
question?
we don't need to find W at all.
Okay, right. So you don't need. So what is the prediction for X test?
Why X test is 1, no?
Okay, does everyone see this?
Sir, could you repeat it?
So what will be the prediction for a new data point? In linear regression, what is the predicted label for a new data point?
It's just W transpose T into XT.
Into X test, yeah.
Right. So now substitute W, the X test as 5 times U. Okay. Is that fine?
Yeah.
Okay, so did everyone get this part? Can I move on now?
Why did the 5 times you? Oh, we just okay. Yeah, got it.
So the final answer is 1.
Yeah, it's just 1.
Yes, the predicted
Some
value
things
is 1.
I didn't understand some things here.
Yeah.
Here, this CI is a scalar.
CI is some scalar, yeah. So according to the convention that I follow, this the things which are not in bold are scalars.
And what is U?
U is some vector, right? So
The
some
vector data point in place of X, Sarah has written U.
It's a single vector, right?
Yeah, it's a single vector, yeah. So Ci times U, see, for example, the one I told before, right? So you are measuring, the idea is you are measuring some quantity at regular intervals of time, of not time, but at regular intervals. So for example, U could be anything, right? You could be, say, the vector 1, 2, 3, it could be the vector -1, 0, 1, or whatever. But it's a constant, that's what matters.
That means each of these data points are basically multiples of the others.
Yes, yeah. They're all scaled multiples of U and also multiples of others.
Okay, so this is a unique data set. It's not a normal data set.
Yeah. Correct.
Thank you.
Sir, I think U is not common for all the data point. When we are saying that there's a multiple of other data, U can be any vector, no, sir. The only thing is what you have done, you have brought up a scalar also C1. That's the only difference. Otherwise, it is a normal X, Y data type only. Are you saying that U is common for all the data points?
I mean, U is the base, right? So C1 times U, C2 times U, they're all like multiples of the same U, right? All data points.
Okay, so here we are assuming that U is common, huh?
Yes, yeah.
So one trivial question, sir. What is actually approach like we did this differentiation, sir? Why we did the differentiation, sir, here?
So we are trying to minimize the loss, right? So we want to find the W which will fit this data set with least error.
Okay, just to find the least W.
Correct, yeah. The W which will give you the least loss.
Okay, thank you.
Okay, so yeah, so now we'll go back to SVM because SVMs are anyway like occupying 2 weeks. So we have a hard margin linear SVM, right? So hard margin linear SVM. Now let's say there are 100 data points, 50 in one class, 50 in the other class. Now you're adding 10 new data points to it, right? Positive data points, and they are all lying on the correct side of the margin, but they are placed very far away from the margin. Okay, so that's the situation. Now you have already trained a hard margin linear SVM for some data set. Now you're introducing 10 new data points, positive data points, and you're placing them on the correct side of the margin, very far away from it. Now you retrain the classifier, right? You train the classifier all over again with this new data set, right? 110 data points are there. So what do you think will happen to the decision boundary of PSVM?
Yeah, nothing should happen, right? Because since
will
they are very far off, they are they're not on the supporting vectors, and as we know that only the points that are on the supporting vector affect that W vector. So nothing should happen, right?
That is correct, right? That is correct. So assume that you have an SVM, a hard margin SVM like this. So these are the existing data points, and you have already trained it, right? So you have already trained it. Now 10 new data points are added here. Okay. So will these data points have any effect on the boundary?
No, sir.
Yes. Right. So this is one way to see it. The other way to see it is a slightly more mathematical way of seeing this is the W star. Okay. The
Alphas will
optimal.
be zero for these, right?
Sorry.
Alphas will be zero, right? For all
Yeah.
these.
Yeah. Right. That's right. So the other way of seeing it will be that W star transpose Xi Ya is already greater than or equal to 1 for these points, right? And especially for these green points is strictly greater than 1. Now, if you add these new points, W star will continue to remain optimal. Right? It will still minimize the primal objective function. Therefore, just adding these points is not going to affect the value of the objective function. It's not going to affect your constraints also. You will, of course, introduce new constraints into the problem, but they won't disturb your feasible region. Okay, is that clear?
Yes, sir.
Okay, so this is yes.
I have one question here, sir.
Yeah.
What's the practical use of hard margin? Because soft margin basically give us a better practical.
Yeah, that's correct. So hard margin is useful so that we can understand soft margin better, right? So if we directly jump into soft margin, intuition we may not have, right? So it's to motivate soft margin that we study hard margin.
Thank you.
Sir?
Yeah.
Yes, this concept is clear, sir. In fact, I was also of the same opinion. It will not have any change on decision boundary. But just trying to establish some relation, I think there is some concept of, that radius of the point, that the maximum distance, right, of the point. And it may be that I'm not able to recall that correctly. And then based on that, we are finalizing our decision boundary. So now since new data points have been introduced, and they are very far from, classifier decision boundary. So will it have any impact on that? Like my radius will also increase now.
No, right? See, the radius first thing is that the radius was an issue. I mean, it was not an issue, but we look at the radius in the context of perceptrons, right?
Yeah.
Right. So now, even in the case of perceptron, if your radius is large, all that the perceptron algorithm is telling you is that it will maybe converge with more number of mistakes, right? Even then, that's all it says, right?
But my margin increases, na? I think if radius is increasing, then my margin increases. Is something like that?
No, right? They are independent of each other. Radius is like the distance of the farthest point from the origin. The margin is the distance of the closest point from the origin.
Okay, got it, sir. Okay, thank you.
Right? Yeah. Okay, so that was a simple question. So we'll move on to the same discussion. Right now, we'll discuss the margin in little more detail. So we have a hard margin linear SVM again. And you are given that the optimal weight vector is W star 1, 2, 3 transpose. What is the distance of the closest point in this data set from the decision boundary? How will you solve this?
Square root 14.
Shall we use that W 2 by norm W? So
2 by norm
what will
W?
that do?
Yeah.
Yeah, so 9 plus 4 is 13. Yeah, I guess that should be the answer. By 2, right? Because that is the width. So we should by 2. So by 4. So that's... No, so that's just 1 by norm W should be the answer.
Okay, yeah, that's correct. So let's.
But sir, in the week 10 at page number 2, in the PDF, I guess it is written that 2 by norm W square. I don't think I'm saying it right here. Uh, it's in the second page of week 10.
Yeah, so that is correct. What you're saying is correct. So Sir, what he has done there is he has solved a different optimization problem, right? So he has also done essentially the same thing, but he has approached it slightly differently. That's all, right? So instead of the, it's different, slightly different. That's all. Nothing else.
Yes,
Okay,
it
I'll
is
just show
what-
you what we are going to do now.
But sir, if we do 2 by norm W square, then the answer will be different, right?
Yeah. The width is 2 by norm W only, right? There's no change in that. So it's not 2 by norm W square. It is 2 by norm W. So what all that I'm saying is, what Sir has written there is not exactly the width, right? He's meaning something else. But when you want to calculate the width, it is 2 by norm W.
Okay, between the two supporting hyperplane.
Yeah.
Okay. So the distance between two supporting hyperplane is 2 by norm W.
Yes. Yeah, we'll come to this now. This is what we'll do.
Sir, can you draw? Sir, can you please draw? Yeah, that's what I want, sir.
Yeah. So see, you have this data set like this, and you have trained the W star, the hard margin SVM, and you get W star that points in this direction. Okay, now these are the supporting hyperplanes. So what is the closest point here? One of these green points or one of these red points, right? So these are the closest points. So let's take one of them. Let's say this green point, which I call xi. So what is going to be the distance of this point from the boundary? Which distance is it? Is it this length of this vector?
No, sir, perpendicular distance, sir.
It should be the perpendicular distance, right?
Yeah.
And that is going to be 1.
Correct. So it's the perpendicular distance, right? So what is this perpendicular distance?
So 1 by 2
Should be 1.
norm W.
1 by norm W.
5 plus 9.
Sir,
1 by
how
root,
can you
1
got
by
the
root
data
14.
point?
1
It
by
is
root 14.
mentioned in the question.
Yeah,
Yeah.
1 by. How did we?
How did you got the data point?
No, this is just for illustration, right? This is not the actual. This is just an illustrative diagram.
It is not mentioned in the question, or it should be the diagram should be appear in the question.
No, diagram will not appear in the question, right? It is not a part of the question. It is just to explain the solution. Okay, so now you want to find this distance. Now, what is this distance actually? It's something.
Gamma.
Right, but what is it geometric?
1 by norm W.
It's the projection.
Yeah, it's the projection of what on what?
Of x1 on the that solid line.
W transpose x is equal to 0, right? That line.
Okay, see, it's the projection of xi, correct? But onto what is not quite clear.
On W.
W transpose x.
X is equal to 0, right? That line.
Right. So see, it's the projection of xi on W, right? W star rather. So that's the important point. Not on the. Of course, the foot of the projection lies on W transpose x equal to 0.
It is a projection on the solid line, right?
It's a you project it onto the solid line, but in terms of vectors, right?
It's W.
This distance is what. Yeah, this distance is what I'm asking, right? So this distance is.
This is the scalar projections of basically the data point on W.
On W, right? That's correct, right? So it's the scalar projection of xi on W. So it is the formula for that is what? W star transpose xi by norm W star. Okay, this is the standard formula. Dot product divided by norm of the vector on which you are projecting. Okay, so you can do something similar for the other side. Okay, why have I written minus here?
Because it is the
opposite direction of W vector.
Correct. So this dot product will be negative, right? So just to make sure that the distances are positive, I have written minus. Okay, so now D will be what? This distance is what we need. What can we say about W star transpose xi?
Equals to 1.
That is just 1, right? So, and you have the formula, right? 1 by norm W star. Okay, Is
And so
this?
in general, we can W transpose X we can say as a gamma, right? So the D will be gamma upon norm of W.
Yes, but gamma in this case we scale it, right? So we scale it in such a way that the supporting hyperplanes are always W transpose X equal to 1.
Okay, if that is the consideration, then it's a 1. Yeah.
Oh yeah, then it's 1. Yeah.
Sir?
Yeah.
So it will be 1 by square root 14, right? It will not
Correct.
be 2 by square root 14.
Yeah, that's 2 by square root 14 will be the width of the supporting.
Yes, yes, that's right. Sir, here this arrow is always W, right? This is my vector, right?
Which one?
This arrow. This,
Arrow is the W. Yeah, arrow is
this,
the W.
then what is this solid line? This is W transpose X, no?
W transpose X equal to 0.
Yes, that is right.
Also, can we say like this? This is width by 2 also it's equal, right? We can calculate in that way also, right? We get again 1 by the norm W, right?
Yeah. The D is width by 2.
Yeah.
Okay, can we move on to the next question?
Yeah, in this example, all data points are correctly classified. If there is any misclassification, then distance will be different, no?
No, hard margin has no misclassification.
So good question. So if there is if you have a soft margin where there are misclassifications, what will happen to the distance?
If
it will still be the same, right?
Yeah.
1 by norm W star is still the margin, geometric margin. So the distance of the nearest, okay, you can no longer call it the distance of the nearest point, right? So in that you are correct, because
there is no question of sign, plus, minus.
So see, the nearest point will change, right? Because there are points which are going to lie very close to your boundary. There are points which are going to lie on the wrong side of the margin and close to you. There could be points which lie on the boundary itself, right? For soft margin. Okay, so you can no longer talk about the nearest point to the boundary and the margin in equivalent terms. Okay, do you get that part?
No, not exactly.
So see, for okay, we'll come to soft margin. I think next question is on. Okay, 2 questions from now is on soft margin. We'll discuss this. But for a hard margin, this is the boundary. This is the margin. Okay.
Yes, sir.
So hard margin will either fail or it won't have any loss, right?
There is no hinge loss for a hard margin linear sphere. Right?
There
So
won't be any loss itself, right? For a hard margin, either it will fail or there will be no loss, right?
there will be there is no concept of a loss function on the data. Yeah, you are right. Yeah. Okay, so a very small digression to regression, and then we'll come back. Okay, so should we do this or should we do STMs? Is what I'm thinking.
Let's do it, sir.
Okay, right. So
even in the exam, we won't have first SVM, then regression. It won't happen that way.
Right. Yeah. So we'll go ahead. So what is this? This question is about a weighted linear regression, right? Where you have a weight corresponding to every data point. So in the loss function, instead of just having W transpose X minus Y whole square, you are going to consider certain data points to be more important as far as the loss is concerned than other data points, right? So I weigh them accordingly. So R1 is the weight of the first data point, Rn is the weight of the nth data point. Okay, so how do you derive the W optimal W for this kind of a situation? Okay, that's the question. Now this is again
we take linear combination with each Ri being the coefficient.
That's correct, right? So we'll do something very similar. So that's what we'll do. So first, I'll quickly go over this, okay? Because in the interest of time, I'll quickly go over this. This is the loss, no? Okay, this is given to you. Every data point.
What are we going to find here?
We're going to find W, the optimal weight vector.
Okay.
So,
sir, can you please explain the questions again?
Okay, see, there are, let's say there are 10 data points. Okay, and for some data points, I consider them more important than others. So for example, let's say the first data point is 5 times as important as the second data point. So R1 will be 5, R2 will be say 1, and R3 will be something else.
Okay, so will be weighted something like in time series that we do, right?
Yeah, it's a weighted loss, right? So instead of just having the same loss for, I mean, the same form of the loss, you're bumping up the loss for some points, scaling it down, so on and so forth.
Got it. Thank you.
Okay, so now again from first principles, what will you do? You will take the derivative. Okay, what will be the derivative for this?
2 W transpose xi, or W transpose xi minus yi
Into
xi into ri.
Correct, right? Only change is that you have a new ri that gets added here. Okay, now I'm going to rewrite this as follows.
Two can be outside, sir.
This two gets cancelled, right? In this case, I've
Okay,
defined.
okay, yes. Sorry, sir.
Yeah. So I'm just rewriting this. Okay, is everyone okay with this?
Yeah.
Yeah, I just swapped xi transpose w, and I have pulled this xi inside. I've just changed few things here.
Sir, I have a question, sir.
Yeah.
So it's a very basic question, sir. So I am confused in this 1 by 2 because usually it is 1 by n in the loss function itself.
So it 1 by n would be mean squared error, right? So it's if you don't add the 1 by n, it's sum of squared errors. If you divide by n, you are taking the average sum of squared errors, right? So it's called MSE, mean squared error.
Okay, here it is.
Here I'm adding a half just for mathematical convenience, right? So if you differentiate, this 2 and 2 will get cancelled when you differentiate.
Even if you had 1 by n, the coefficient outside would be 2 by n, but because you're setting it to 0, that will anyway vanish, right?
Yeah,
Doesn't matter.
correct.
The derivation will not matter.
Right, right.
That will vanish, Vasu.
This
Vasu,
once
that will
again.
vanish, but that will be mean error, and here it is square error. So there is a difference.
Correct. I'm saying mean square error
Here it is still sum of square error. I think he is getting confused 1 by 2. So this was discussed in one of the class. This is just to facilitate the derivation part. This is the way we are defining our law. That's it.
Okay. But in the real part, we have to take the 1 by n now in the exam.
No, when we are taking 1 by n, then it is a mean square error. And when we are not dividing by n, then it is still sum of square error. No? Just see sum of square error. You are taking error, you are squaring it, and then you are adding it.
Okay, got
this 1 by 2 has been added only to cancel out that 2. When we will take the derivation of x square, so it is nothing but 2x. So you are getting a 2, so that 2 and this 2 will get cancelled. That just to facilitate.
Got it. Okay.
Sir, I
Excuse me,
have a
sir.
query here.
Yeah.
Sir, see here we are taking the weight as from R1 to Rn, right? So it will be like the h of x will be nothing but R1 x1 plus R2 x2. It will be of that format, no sir. Then why do we again take W transpose here? Because
No, right? So h of x is still W transpose x, right? See, the when you say weighted linear regression, what I mean is the weights are applied only for the loss function. Okay, the weights are only for the loss function, not for the actual model. So the model is still W transpose x. Okay.
so weight is, I mean, R1 values or along with the weights you are telling, like the multiples of weights you are telling.
So the R1 value is nothing but the importance of that ith data point. Ra is the importance of the ith data point when it comes to the loss computation. That is all.
But we
Okay,
shouldn't consider that with respect to original models. Sir, see, generally h of x will be like weight 1 into x1 plus weight 2 into x2 plus weight 3 into x3. So I thought you told that R1, R2 are the weights, right? Weight for each data point. So
okay, yeah, this line is a bit
I just
misleading.
don't understand actually. Yeah, that's why I'm just asking, sir. Weight for.
Yeah, so yeah, this is the weight for each data point in the loss function. In the loss function. Maybe if you add that line, add that phrase, it will become more clear.
Okay, so we should take Ri along with W transpose Xi only. I mean,
see, W transpose Xi is the prediction for the ith data point, right? No change. That's the same good old linear regression. Whatever it is, it's the same thing.
Okay.
Ra is just
so to your question, when you're taking hx, you shouldn't take ri there.
that's what I got confused here because
You shouldn't take Ri there. Ri is just while you're computing the loss.
Okay.
Yeah,
Okay,
just
sir.
one thing.
Somehow it's just
Can you
confusing.
just
I'll just go through it once again.
Yeah, go
hi?
on.
So can you just explain that first term RIXI times XI transpose? Where did the XI transpose come from? Another thing.
This one. This
Uh,
one.
yeah, and also if I have XI times XI, can I always write it as XI times XI transpose?
See what I've done here is I have swapped W transpose Xi and I have swapped W and Xi because it's a scalar, right? I can either write it as W transpose Xi or Xi transpose W because it's symmetric, right? The dot product is symmetric.
Oh, and after that you have just
Brought in the Xi inside, that's all.
XI. Okay, yeah, got it. Thanks.
Okay, so this once you do this, right, and here is something that I'm just going to. So this is your usual X and Y, right? The data matrix and your label vector. Now R is this diagonal matrix, right? So I'm going to multiply X and R. So if I multiply X and R, what will I get in each of the columns?
XI RI.
Correct, right? You will get Xi Ra. So you'll get R1 X1, you'll get R2 X2. Okay, I'm not going to do this computation now. You can verify this later, right? So if you multiply a matrix X with a diagonal matrix, each column gets scaled by the diagonal corresponding diagonal value. Okay, this is some it's an exercise for you later on. Okay, for you to do later. So if I plug this
Sorry,
in,
I can understand how do we came to XR.
I am giving this to you, right? So
Okay, I'm so sorry. Okay.
yeah, you can use this as a trick, right? For later on when you come across sigma xi ri kind of thing, you can invoke this particular operation.
Okay.
Okay, now is this familiar to you? So you have something into something transpose. Where have you seen this before?
So this is in that. I'll tell you.
Covariance matrix.
Okay, this is some kind of a covariance matrix. So
Yes.
how will I write this down now?
So this time I will write Ri by N C.
Okay, see.
You can write this as xy into ri r.
Right. Okay. No, this part, right? Left hand side part. No, left hand side summation becomes what?
XR. So the whole thing becomes XRY caps.
Some scaled version.
Okay, so I'll write it down in the interest of time. Later on, you can tell me if you agree or not. Do you agree that this whole gradient expression will become?
Yeah, xr. Oh, yeah. Sorry, did I say xy alpha? Okay, xry, correct.
Okay, this is like I have telescoped several steps into one. So I'll let you work on this, right? I'll let you think on this.
This comes in that dual problem derivation also, sir.
Yeah. This summation comes in the dual problem of SVM. Now, so once you have this, how do you find W? If it is this matrix on the left is invertible, you just do this, right? For a moment, assume that R is identity matrix. What if R is identity matrix? What does that mean?
So this is basically
It's just normal regression.
Yeah, simple. The whatever we know, right? Normal linear regression, right? So all weights are equal and they are all one. So it's the usual XX transpose inverse XY. If you have a set of weights R1 to Rn which are not which are not 1, then you introduce this extra weighting factor called capital R. That's all. Okay, so that's how you understand this expression. Now, some aspects of this solution may not be clear now, but again, it's just algebra. So
We are not doing treatment of second components, Ri, Yi, Xi.
Ri, Y, Xi is what? You just multiply this XR with a Y vector, right?
Yes, and then we have to multiply it by Xi also.
Sorry, and then what?
Xi is there as a third part. Ri is there, that's a weight vector. Yi is my label vector, right? And then Xi is my data point.
Right.
So why we are not doing simplification of that part? That's my question. Like this part is clear. We got XR H transpose inverse XRY.
This we are not simplifying further, right? So
okay, we are not simplifying.
Yeah.
I'm sorry, I didn't get this. We've gotten W as this, and it's as if it's the same formula, except that we're multiplying each of these terms by R, right?
That's all. Yeah, that's the way to
So
understand
what kind
it.
of conclusion do I draw from this? That is what I'm not able to understand.
Yeah, see, if R is identity, that is if all the weights are unit values, right? Then it means you go back to linear regression, XX transpose inverse XY, right? If R is the identity matrix.
Okay.
Now, if R is not the identity matrix, then you are going to this XR term will come in here, right? So depending on which
It will come into the computation of W.
Exactly. That's all you need to know, right? It will come into the computation of W, and that is how it will impact your final weight vector.
Okay, so since we're giving different losses, different weights, if the weights are not equal, then it will affect our final weight vector.
Right. That's correct.
So what is the end objective of this question? Like what this question is going to solve?
Okay, so this is just a demonstration of how weights affect the
okay.
linear regression.
Yeah.
Sir, what if R was? I know it's not meaningful in that sense, but let's say R was not an identity matrix, but let's say 2 times an identity matrix. Does that change anything?
No, right? Because this is just like scaling it, so it shouldn't change.
Scaling, except that inverse. Yeah, it gets adjusted in the inverse. Correct.
My question is actually I still did not understand these questions. Reason being, the RI is not the weight of the data point, right? It's
It
the
is not
weight
the weight
on the loss.
Correct.
I'm not been able to relate it practically. Where can we relate it?
See, you have this in certain instances where there are certain problems where there is this okay, this is not true for regression, but let's take the case of classification where you have the situation called class imbalance, right? So the situation of class imbalance data set would be something like, say, you have 100 data points, 90 belong to class 1, 10 data points belong to class 0. Okay, so in such a situation, if one approach to mitigate this problem of imbalanced data set is to bump up the factor of the contribution of the loss for the 10 data points.
Understood.
Right? So if you are going to give the same weight to the 90 as you give to the 10, then it means you are.
What happens if we give the weight to the data point itself instead of giving weight to the loss function? Will the problem remain same, or?
So what would that mean, right? In terms of practically, what does that mean? What do you mean by weighting a data point? You are completely altering the data point, right? You are making the data point 3 times xi. So that's like you are multiplying each feature by 3. So is that a valid operation? Yeah. So.
Okay, and
thank you.
I'm just interrupting here. Since Dheeraj he asked, this is weighted least squares, and this is, and Sir said that this is not relevant for regression, but it is indeed. It is used to solve a problem called heteroscedasticity. So if someone is interested, they can look it up. It's a problem where the disturbance term does not have a constant variance. So to solve that problem, we use something called weighted least squares, and this is where it comes up. So this is in econometric analysis, but yeah, so just wanted to share that.
Sure. Thanks
for that insight.
Okay, so this is Q8. Now,
so how many questions we left?
I have 14 with me, but we won't be able to do 14. So let's do maybe one more or two more and then close it today.
Okay.
But we will continue with the remaining 5 some other day, right?
Yeah. Before, maybe Monday. I don't know Monday or not, whether it's Monday or not, but yeah, sure. Usually finish off these things. Yeah.
Thank you.
So can you please request everyone to mute if they are not talking because there's a lot of disturbance.
Yeah, thanks. Yeah, sure.
Thank you, sir. Thank you.
So we have a hard margin linear SVM. What did we do last? Yeah, we did equation. Now we have a hard margin linear SVM, and the optimal weight vector W star is 2 minus 1. Okay, so and you now have a unit square, right? Unit square is a square with unit side length, and the corners of the square are at 0, 0, 1, 0, 0, 1, and 1, 1. Okay, so the question is, you pick a point at random actually from the square. I didn't specify that, but you pick a point at random from this unit square, that from within this unit square, and you pass it through the SVM. What is the probability that this point is going to be classified as 1?
I solved this, I got 0.75 as well.
Right, yeah. So we'll come to that answer. Before that, for those who are seeing it for the first time, how do you approach this?
We can take a graphical approach, right? So if you just draw and if you plot W transpose Xi, then
Correct, yeah.
we can.
So the graphical approach is one we use. So this is what the problem is telling us, right? So you are having a unit square at the corners of the corners of the unit square are given here, and somewhere from inside the square you are picking a point at random. Okay, so you need to find the probability that it will be predicted as 1. So what's the next step before we go to that? What should I draw now?
We should draw the decision boundary.
Right. So you should first draw W star, and that is given to be 2 minus 1. Now, how do I know how do I draw the decision boundary in this case?
Take the perpendicular.
Okay, how do I compute the perpendicular for this? What will the equation be?
Yeah, so W transpose Xi should be 0 orthonormal. Yeah.
Okay, so can you tell me the equation
Yeah,
of the
so
line?
2x1 so
minus
if you take x1
x2
as x2
equals to 0.
Right, so x2 equal to 2x1, right? So when x1 equal to 0.5, x2 will be 1. And when x1 is 0, x2 is also 1. So if you connect those 2 points, you will get this line. Okay, so this is the decision boundary.
Sorry, could I just interrupt? So it's 2x1 is equal to x2.
2x1 minus x2 equal to 0, right? W star transpose x equal to 0. So 2x1 minus x2 equal to 0. So
yes,
x2
2x1 is equal to is equal to twice x1.
Yeah, x2 is twice x1, and then you plug in 0.5 and 0, you get 1 and 0.
Okay, thank
you join those two, you get this line. Okay, now which area are we interested in? So
the one on the right.
Below, yeah, below.
This is the one we are interested in, right? So this is the entire region will be green, but we are only interested in what part of the square will be green. Okay, so now this is the area we need to compute. One way to compute the area is look at the square's area and subtract this small triangle, right? So it is 1 minus half into base into height, right? So it is 1 minus 0.25, 0.75. Did everyone get this part?
I have one question. What happens to the margin here?
So
this is a decision boundary, right?
Yeah, the margin is 1 by norm W star, right? That will still be there.
Okay, so if we include the margins, shouldn't the area becomes a bit less?
No, right? That's the margin is only for the training part. So the margin doesn't feature in the prediction
okay,
part.
this is for predictions. Okay, got it.
Sir, can you please explain the last data? 1 minus half into 1 into half.
So this green area is clear, right?
Formula for a triangle is half base into height.
So the green area is what? The square's area minus the small triangle here. So what is the area of this triangle? Right triangle?
Oh,
half base. Okay.
Half into 1 into half, right? So
So
From
basically,
what I figure, I think most of these problems are solved better when you have a geometric visualization of them. So I think we should get graph paper as rough papers.
Right. So yeah, but yeah, geometry helps. Yeah. So
yeah,
that is correct.
So Nijam will
So
get
the
graph
only
paper,
way
sir.
of approaching this type of question is the graphical way,
This in this particular case, yeah, there's no other way.
because
Or
yeah,
at
this is much easier also. Is
yeah.
there any way normally?
Normally, let's see, W star. See, you can do integration if you really want to push it.
That will be common. So better to go with this approach, right? Draw
Yeah,
and check it
yeah,
out.
yeah.
Okay.
Sir, did you mention that we have to take points from square only? Because I
No,
have
I didn't mention it. Actually, I should have mentioned it.
Yeah, because as per the normal convention, all the regions on the right hand side belongs to +1, right?
Yeah, yeah, that's correct.
Okay. Anyhow, it's a good question.
Okay, so this is an NSEM question. So this we asked in, I think, last NSEM. No, not, I don't know when, but we asked this sometime.
sir, I have a question. Sir, I joined late this session. So, sir, this end term
So
revision for
sorry, one second, sorry. But this question is asked in the set of questions you've given, right? So,
Yeah. So that set of questions has.
there it's very clearly mentioned. It's like within the square. You pick a point from within the square.
Right.
Good. You were saying something.
Rohit was
yeah,
saying, yeah.
Rohit.
yeah. So I joined late. So this session is for, sir, all the weeks, or it is for few weeks? I mean to say, for which weeks this session?
Session is like more of a practice problems, right? So I'm just covering weeks at random with more weightage to the last 4 weeks.
Okay, got it. And sir, the end term exam should be, or it will be 50 to 60% weightage from the last 4 weeks.
Yeah,
And
60%.
okay, and sir, remaining. Okay, got it. 1 to
Yeah.
8 is 40%.
Correct.
Okay.
Right. So maybe I'll just do one last problem, and then we'll close here. Right. So this is, I think you all already have seen this, but
We can continue, sir. We can finish.
yeah. So there are two statements, right? So
What? First one is true, second
One
is
is
false.
correct and second
First
is
is
wrong,
false,
right?
second is first is true, second is false.
Yeah, correct.
yeah. Right. So let's just quickly go over this. I just want to use a different configuration of W, right? So I think someone asked at the beginning of the session for this particular configuration, how can we have the weight vector pointing in the third quadrant? And
The only thing is better to qualify that this is for hard margin.
Right. So the next question is on soft margin. So that'll maybe we can take it up on during the next session. Right? Yeah, this is true. This is true only for hard margin.
I have a question.
Yeah.
Here, in hard margin SVM, is it possible that a point is correctly classified, but it is between the margin, that is the support hyperplane, and the decision boundary?
No, right? That is not possible.
It's not possible.
Yeah.
Thank you.
By the very design of the algorithm, we want all points to lie beyond the margin.
Okay.
Right.
Okay. Yeah.
So let's quickly go over this. Why this is true? Why first one is true and second one is not necessarily true? So this is the constraint, right? For each data point, you'll have this constraint, and you write it as 1 minus W star transpose XIOA less than or equal to 0, right? So you do this, and then what is this expression here? Where do we get it?
So
from?
this is a constraint. I think G of X. No, the constraint
Yeah,
we
so
defined.
alpha is the Lagrange multiplier times the complementary slackness condition.
Correct, right? So this is the CS conditions, and alpha I star is the dual optimal value for the ith data point. This is the ith primal constraint. Okay, so you take the product, and that comes out to be 0. Now, what does the first statement say? Every support vector lies on one of the two supporting hyperplanes. So we are talking about support vectors. So what is the definition of a support vector?
The points which lie on the
Is that the definition?
Alpha is 0.
Yeah. So this is the important catch, right? It's very important to note this. The definition of a support vector is points for which alpha I star is positive, right? This is the definition of a support vector. Okay, why is this the definition? It's because these are the ones which contribute to building your weight vector, right? Your weight vector is what? Sigma alpha I xi ya, correct? Alpha I, sigma alpha I xi ya. So if alpha is 0, then there is no point calling it a support vector. So the definition of a support vector is that point for which the Lagrange multiplier corresponding Lagrange multiplier is positive, right? Strictly positive, not even equal to 0. Strictly positive. So if alpha I star is strictly positive, what happens to the constraint? It has to be 0, right? So W star transpose XIY has to be 1. It means every support vector has to lie on one of these two supporting hyperplanes, right? That's the first statement and it's true. Now, how do we argue about the second point? Every point on one of the two supporting hyperplanes. So what is the equation that I'll write here?
Sir, if a point is on the supporting hyperplane, then it is not necessary that it should contribute because its alpha could be 0.
Correct, right? So if a point is on the supporting hyperplane, what does it mean mathematically?
W transpose X is equal to 1 or minus 1.
Correct, right? So let's just write that down. So W star transpose Xi Ya will be equal to 1, right? If a point is on on one of these two hyperplanes, supporting hyperplanes. So if this is true, then the G of Xi, right, the constraint is 0, but that doesn't give us enough evidence to conclude that alpha I star is 0. So this does not imply that alpha I star is equal to 0. Okay, this implication is not true. Therefore, second statement is false, right?
Yes.
Every point on one of these two supporting hyperplanes is not necessarily a support. Okay, so that's we'll stop here. The next question is about soft margin, and we will discuss several of these things there. So
Just a question, small question.
yeah.
So if you are asked to identify if something is a support vector or not, then then we should basically look into alpha i's, right?
Yeah, that's the test, right? That's the acid test for determining if a point is a support vector or not.
Okay.
Sir,
And I
one
would
more thing.
presume in case of soft margin, we'll have to also look at beta i's.
No, in the case of soft margin, is it? Even
Yeah.
there, even there only alpha is matter, right? Because the W is still
Yeah,
sigma
alpha
alpha.
I plus beta equals to C, right? Okay, okay.
Sir?
Yeah.
I think in one of the revision session, this was discussed that even a point is in between hyperplane and decision boundary. So
Yes,
that will
for a
definitely
soft margin that will be
a supporting
considered.
vector.
Yeah,
That will
for
definitely
a
be a
soft
supporting
margin
vector.
SVM that will be considered as a support vector.
Okay, but not in a hard margin.
No, hard margin does not have any points between the hyperplanes, right? Either the point
Right.
is on the plane, is either on the supporting plane or it is away from it. It is not between the decision boundary and the hyperplane because the algorithm for a hard margin does not allow for that.
Right. But in soft margin, the point can be in between
Yes. In
decision
soft
boundary.
margin, if the point is in between, then it is going to account. It is going to have a positive alpha.
It will
Not
definitely have a positive alpha.
yes,
Yes.
Yes.
So anything not just between the hyperplanes, also the ones which are misclassified.
Yeah.
Yes, even if it is misclassified. Yes.
Correct.
Sir, one question.
Yeah.
You guys uploaded the end term practice set 1, right?
Yeah.
And I think I saw on the forum that there is another set of questions to be released soon. When would that be happening?
It was in mail, yeah.
Yeah, so that also will be. So I have just hijacked some questions from there into this particular set.
So which
So,
will be released?
no, it's not released. I have to release them, but you
okay.
won't find 20 new questions, right? So you'll find some.
Yeah, sir. No worries.
Sir, are we going to discuss the questions all the time? I mean, all the sessions, or like theory also going to discuss, sir?
Theory we can discuss, but it's like, yeah, we can discuss some extent if you want but we have already gone over it, right? All
Are
of
we not going to cover remaining parts, sir? I think we have read only up to 98 and I think 145 pages are there.
Yeah, but we are already kind of. If you want, I can do one more question. That's on soft margin
Okay, no
SVM.
problem. I think many people have dropped off.
Yeah.
And
So
so this session contains all the weeks, no? All the weeks question.
not all the weeks, some of the weeks, right? So maybe half the weeks you could say.
And so the next revision session is on maybe on Saturday, or because in calendar it is
No,
showing it is on.
Saturday will be too late, yeah? Saturday will be too late.
There is one session on 26th. And then the last revision session is scheduled for Saturday.
We'll have
As
one
per the
between.
calendar.
I don't know
No, that
when
Saturday
to.
session will be for mock test, I think. Sir, are you going to release mock test also this time?
No, sir. 25th, sir, there is session interaction with
No,
Professor Arun.
26th, yeah, Professor Arun.
25th, yeah, 6 to 8. And so the last revision session 2 will be on Saturday, 29. According
No,
to the calendar.
we'll have one between. So, like
Oh.
say Wednesday and
Then
Saturday.
Monday we can
Or
think of,
Monday.
sir.
Monday
Monday
is
we can think of, yes, sir.
So you can take tomorrow also, sir, because it is Sunday and for working professionals it is good. Anytime on Sunday. Tomorrow.
Sunday, see, I have only 4 more questions to discuss, so I cannot be like significant. If it's Monday, I can maybe add 2 or 3 more questions and make it.
Monday is
So
that
for
okay.
would be
Monday works then.
beneficial.
Monday evening would work.
Question will be one part, sir. If you have time, sir, could you please cover week 8 also, sir? Just to slight extent, like Gaussian base and
Okay, yeah, we'll look into it.
naive base and Gaussian base. That we,
Sir, also like from week 2, I think so, there is a kernelization, okay, actually concepts. So if we just briefly discuss that also will be good, sir.
Yeah, I have a set of slides on kernels, right? I have a bunch of slides on kernel regression and kernel SVM and what are their differences, similarities. Yeah, so we can do.
kernel as an independent identity, sir, because kernel is coming everywhere. Kernel PCA, kernel regression, kernel clustering, kernel SVM.
Yeah. So we'll do that. So for unfortunately, for kernel PC, I can't do much because in terms of bringing out some graphical or visual things, it's very tough for kernel PCA. But for kernel regression and kernel SVM, I'll show some things.
I think Ravi was saying something. Let him complete, then I will say, sir, what I wanted to. Yeah, Ravi, you are saying something. Ravi, you are saying something? Okay, sir, when we talk
Reason there in the meet.
Sir?
Yeah.
When we talk about this kernel PCA, right? PCA, if you see, professor started with the concept of PCA, then he said that there are 2 major issues. One is with respect to complexity, and then the other issue is with non-linearity, right?
Right.
And then he said that to address both these problems, one solution will satisfy both, will answer both the problems. And then he started with a feature transformation, and then kernel function and kernel matrix there. So we don't want that geometrical interpretation and all, but at least this connectivity, like from where we are getting those functions, 5x, point number 1, and then kernel function and kernel matrix kind of thing. And I think everywhere, whether it is coming in regression or clustering, the main objective is to convert from non-linearity to linearity, right? That's the main objective.
Right. That is kind of good enough, right? So you want to know why we are using these kernels in the first place. Is that what you want?
No, from where we are getting that function. When he's saying that we have to find out a function, so how to get that function, and then some alpha also comes into picture. I don't think that the entire concept is blank. I think a couple of more people raised questions related to kernels. So even some touch base.
Okay, so this is, you see, we'll do this, right? So make this the first question, or make this one of the important questions for Tuesday's session, right? So that maybe Sar will be able to give a much better idea of the basis for all kernels, right? So if you ask me, about the genesis of kernels and all that, I don't know, but he will be able to give you exactly from where they come and some more insight he'll be having, right? So it might be a better idea to ask this particular question, right? During Tuesday's session.
And sir, even in EM algorithm, sir, expected maximization, right? there are two steps. So, sir, there are, I think it's related to Gaussian mixture model. There are many Gaussian models, right? So, my question is that when we talk about this mu, sigma means variance, sigma square, and then cluster number, right? All these are unknown. We further introduce one more parameter, lambda, like probability of ith element going into one particular cluster, right, or different cluster, right? So we are differentiating by fixing one at a time. By fixing lambda, we are differentiating to find out other parameter, and then we are fixing other parameter and differentiating with respect to lambda, right?
Right.
So my point is this, that when we don't know about any of the parameter, then how we are fixing it?
This is iterative, right? So, for
Pardon?
example, in
It is
iterative, right? So, in any iterative algorithm, you, for example, gradient descent. So, you don't know W, but you start with some guess W0, W0, right? And then you evaluate the gradient for the next step at W0, right? So, and then you find W1, and then you once again evaluate the gradient at W1 and you update W2, so on, right? So, any iterative algorithm assumes some starting point, some initial starting
okay.
point.
We are not supposed to know the exact value.
The hope is that if the iterative algorithm has some guarantees, convergence guarantees, then you will converge to at least a local optimum.
Okay, so since it is an iterative algorithm, that's why we can proceed like this, right?
Right,
And
right.
so then what is the difference between lambda ik and pi k? Because lambda ik is probability of one element, ith element, getting into one of the cluster, right? So say
Correct.
for example, there are three clusters. So my same element, say for example, I picked up x1. So it has a probability to go into pi1, it has a probability to get into cluster 2, it has a probability to get into cluster 3, and
Right.
all will sum to 1, right?
All
So this
the
all will sum to
right,
1 because
correct,
all lambda I will sum to 1. Then
correct.
what is this pi I? This probability of cluster 1.
That is
Pi,
the
pi i
mixture
is
probability. Right?
pi I is basically the likely size of the cluster. You can think of it like that.
So
Yeah,
it's the
लेकिन what is the
prior.
probability? Sorry, that is also a probability. Na? Pi I is also a probability of cluster 1, right?
Yeah, you can view that as the prior probability, right? So if you want to pick a point at random from the mixture, what is the chance that it comes from the ith cluster, ith mixture? So that is pi.
No, at the beginning, when professor was setting that experiment, he said that he is having a machine, and machine is having three phase die, right? So say for example, he will pick up point x1 and he will press the machine. And
Right.
say for example, if pi 2 comes, cluster 2 comes. So my x1 point will go into cluster 2, right? This was
You
beginning
will
of my experiment, but later on when he introduced lambda I, then he said, lambda ik is the probability of ith element getting into the kth cluster.
no, not getting into, right? So coming from the kth cluster.
That both means same, no, sir?
No, see
It does it. One is prior, one is posterior. You can think of it like that.
Right. So see there are three boxes, and then ideally what is happening? So the data points are drawn from one of these three boxes, right? And how you pick the data point initially depends on pi 1, pi 2, pi 3, right? Now someone gives this xi to you. Now you're asking, you don't know. In reality, these zi's are hidden, right? That's why it's called a latent model, right? Latent
variable model.
Yeah.
Latent
So
variable
because you don't know where the exact point came from, all that you can say is, given that I have a point, the probability that this came from this particular mixture is so on and so forth. Right? That is the lambda ik.
So what you are that in the simplest form, I can take that one pi I is the prior probability and lambda is the posterior.
Posterior, right? That's correct.
Anyhow, sir, I'm not clear, but let me think over it. Again, I will come back.
Yeah. So see, you please
Sir, I
ask.
have
Yeah.
one.
Yeah. Go on.
Yes, sir. So you said that it is iterative algorithm. So, sir,
Yeah.
I have a question. It is a confusion, not a question. Sir, in the ANNs, sir, we use the initializers, just like he initializer, normal initializer. So I think, sir, to prevent this, that randomly choose the point, we use that thing now.
Sorry, to prevent what?
To prevent randomly choosing the any initializing point in the iterative algorithm.
Okay, why do we choose particular initializations in neural networks? Is it?
Yeah, sir. Yeah, that is he initializer or normal initializer or whatever it is. There are many initializers, I think.
See, one thing is you should not initialize everything to 0. Okay, that is one rule of thumb, because then basically everything will end up, all neurons will end up learning the same things, right? So you initialize your weights differently, but to my knowledge, different initializations are heuristics at the end of the day. I don't know if there is a very principled, proper mathematical backing for, but there may be, right? I don't know. So deep learning course will address this better.
Okay, sir. And so one more thing, sir. Sir, the session for the AN and all the things will be later now. It is the next session or the last session, the week 12.
So week 12 session is already there.
What's sir?
This it
has been
happened.
conducted, Rohit. It has been conducted. That's what it's saying.
No, for the revision purpose.
So see, that's the point, right? So there is, I can do a repeat of what I did on Monday, right? Monday was the revision, like the week 12 session. Essentially the same thing I'll have to do. So
I think that is sufficient. Whatever we did on Monday, na, because only 2 lectures are there on a neural network.
yeah, so please you can watch that, no, because it's like.
Okay. So okay. And
I'll
sir,
end up repeating myself. Yeah.
Yeah, sir, it's okay. Okay, if you can brief us in the revision session, it is also no, not the entire, now, not the whole thing, only the 15 minutes or 20 minutes.
Yeah. So there will be questions on week 12 in the. I have some questions on week 12 as a part of this, right? So we'll.
That is sufficient. That is sufficient for us, not the entire revision. And so one more thing, sir. There is overall 3 sessions now for the end term. That is, one is today, second is Tuesday, and last one is, I think, maybe Saturday or Friday. Right now it is Saturday.
Monday, I think we'll do one more. Just the time alone is we need to fix. But
that 8 to 10 will be okay, sir.
Right.
So Monday and the last one is on the with the sir, Professor Arun.
No, we'll have one more, right? For week 11 and 12. So not 12, but for few other weeks we'll have one more on
week 8, sir. What we are discussing, kernel and week 8. Yeah.
So except sir, Professor Arun, sir, we have 3 sessions, no? If we exclude that.
Monday is one, Tuesday is one more, and then probably Wednesday or Thursday will be
one more.
So, yeah, at least 3 more we'll have.
Okay. In total, we have 4 revision sessions for end term.
Yeah.
Okay, got it.
Okay, I'll just stop the streaming now and can also close the meeting.
Sir, just last question from my side for today.
Yeah.